Hello, so today we will learn about the second isomorphism theorem. Before doing this, you will notice that we have put the number second over here. And the last theorem that we did, that is the fundamental theorem of group homomorphism. We will call that one as the first isomorphism theorem. Let me just say one thing, that there is no agreement which one is the first isomorphism theorem, which one is the second, and which one is the third isomorphism theorem. Different authors use different numberings for the theorems. But over here, we will call this one as the second isomorphism theorem. So let us just see the theorem. What does it say? And we will prove it. H is a normal subgroup of G. K, it is just a subgroup of G. Then we will have that K by H intersection K is isomorphic to the quotient group HK over H. So if we have to prove this one, we will have to use the fundamental theorem of group homomorphism. That is the first isomorphism theorem. We will no longer go with the definition by defining a function which is 1, 1 on 2 and a homomorphism, but we will use the fundamental theorem of group homomorphism. Before doing that, let us just say, so if you have that H is normal subgroup of G, K is subgroup of G, and also so we can immediately see that H intersection K, it will be a subset of K, and because intersection of two subgroups is a subgroup, so H intersection K will also be a normal subgroup of K. That is why we can form this quotient group. Similarly, we have done in the exercises that H will be a normal subgroup of HK. You can refer to the exercises of why we are able to form these quotient groups. So over here, the proof I will write clearly, but sometimes it's not so clear. Clearly, H intersection K is a normal subgroup of K, and H is a normal subgroup of HK. You can refer to the exercises. So now what we will do, we need if we have to show that X by Y isomorphic to Z, what do? We will define a function from X to Z. So that is what we will do here too. We will define a function from K to HK over H. Number one, that is the first step. Define a function f from K to HK over H. So this function, define it as fk. It takes an element k which belongs to K. It will have to be an element of HK over H. So how does an element of G by H looks like? If you remember, an element of G by H, it looks like HG, where G belongs to G. So similarly, an element of HK over H will look like H and an element X, or maybe HX, where X belongs to HK, but where X belongs to H, capital K. This small h comes from over here, and this small x comes from the numerator, that is HK. But if X belongs to HK, then you can write it as h small k. If you remember, H can be absorbed in this capital H. So ultimately we will be left with H small k. I hope it is clear. So we will define it in this way: Fk equal Hk. I will just erase this. So now what do we need to do? We need to show that it is well defined onto homomorphism. At least that is what we will do first. Well defined. let k1 equal k2 belongs to k, we will show that hk1 equal hk2 or fk1. But if k1 equal k2, we can have hk1 equal hk2. So in other words, we will have fk1 equal fk2. So this is done. This is well defined. Number 3, what we will do is we will show that f is a homomorphism. Let k1 k2 belongs to k. F k1 k2, how much will it be? It will be h k1 k2. But because it is normal, because h is a normal subgroup of G, you can write this one as h k1 h k2. You can write this one since h is normal in G. So we will have f k1 f k2. So that is why f is a homomorphism. The fourth thing that we need to do is we will show that f is on 2. Let y belongs to, if we need to show that it is on 2, we first have to take an element of the second set. The second set over here is hk over h. Y belongs to hk over h. We need to find an element which is a pre-image of y. So if y belongs to hk by h, we will have this hx, where x belongs to hk. But x belongs to hk, you can immediately write this one as hk. H belongs to h, small k belongs to capital K. So you will have it equal to, again, h can be absorbed in this capital H. We have done that already. So you will have hk. So by taking this k over here, which belongs to capital K, which k is the first set, we have fk. Fk, according to the definition of the function, it is hk. So it's equal to y. So we can find an element k that is a pre-image of this y. Hence, it is on 2. Next, what we will do is this. We have managed to define a function that is on 2 and a homomorphism. We will show that this one, h intersection k, it is equal to kernel of f. So the fifth part, proving h intersection k equal to kernel f. So both of these are sets. So the first part consists of proving h intersection k subset of kernel f. So how will we do? That x belongs to h intersection k implies x belongs to h and x belongs to k. Now we need to find fx, because we need it to be in the kernel. If you need to show that x is in the kernel, you need to find fx, and we will show that it is equal to the identity. Fx, how much will it be? According to the definition, it is hx, right? It is hx according to the definition. Let's see, define. Fk is hk, so fx will be hx. So that is clear. But x but x belongs to H. X is an element of H, so it can be absorbed in H, since X belongs to H. But this H, it is the identity of HK over H. How do you know that it is the identity of HK over H? Because if you remember, we have done that. The identity of G by H, it is just capital H or HE. HE or just capital H. So that is why. So that's also why the identity of HK over H, it is just capital H. So when we get something like this, it means that X is sent by F to the identity. Hence, X belongs to kernel F. Now we will do the second part, that is proving kernel F subset of H intersection K. Let X belongs to kernel F. Since X belongs to the kernel F, it means that X, first of all, it should belong to K, and Fx, it will be equal to the identity, that is equal to H. Implies X belongs to K. Fx, according to the definition, it is Hx. So we will have this Hx equal H, Ha equal Hb. We will have AB inverse belongs to H. So Hx equal H, or we can write it as He also. So we will have AB inverse belongs to H, but over here we will have X E inverse. So E inverse belongs to H, or simply X belongs to H. Therefore, X belongs to K and X belongs to H, so it will belong to H intersection K. So we will have this. So once you have that, you can conclude by fundamental theorem of group homomorphism. We have so what will we have? We will have K by kernel F. K, the first group, over the kernel, it will be isomorphic to the second group, HK over H. That is kernel F, it is H intersection K. So we will have this, which proves the theorem. So I think that is enough for today. I will also be sending notes on the third isomorphism theorem.